So we're going to take a look at alkenes and conformation. This is the next step after our study of alkanes. So we're going to be looking at conformation, which is any three-dimensional arrangement of atoms in a molecule that results from rotation about a single bond. So if we think about a staggered conformation, that's a conformation about a carbon-carbon single bond where the atoms on one carbon are as far apart as possible from the atoms on an adjacent carbon. So on the right is a Newman projection, and if you take a look at the side view of a molecule, if we rotate that so it's almost on its end, and then turn it so we see the end, you can actually see the staggered conformation where everything is spread as far apart as possible, and you can see the way that that's represented by a Newman projection. If we take a look at the eclipsed conformation, that's a conformation about the carbon-carbon single bond in which all atoms on one carbon are as close as possible to the atoms on the adjacent carbon. So literally everything's on top of or as close together as possible. The reason why we study conformation of alkanes is because it connects with energy. So a fully staggered conformation is the lowest energy conformation of an alkane. And we care about this because torsional strain is the strain that arises when a non-bonded atom that's separated by three bonds are forced from a staggered conformation to an eclipsed conformation. So that's the energy it takes me to rotate this molecule from staggered to eclipsed. It's also referred to as eclipsed interaction strain. And if we want to think about numbers, the torsional strain between staggered and eclipsed ethane is approximately 12.6 kilojoules per mole, or 3 kilocalories per mole. So take a moment, we're going to draw as many conformations of butane as possible. And if you need to, press pause so you have time to do this exercise. Take a look at all of the possible conformations. Notice there is some overlap. So these two are the most stable. These, right, are less stable. These are, again, more stable. And this is the least stable. And I can see that here because the low energy wells, so this is most stable. Again, these lower energy wells correspond to a staggered conformation, whereas these high energy points correspond to eclipsed. Cyclopentane is where all CC bond angles are 108 degrees, and that differs only slightly from the tetrahedral angle of 109.5. So there's going to be very little angle strain. Angle strain is what arises when a bond angle is either compressed or expanded compared to this optimal value. So take for a moment cyclopentane as an example and draw three different representations and think about angle strain. So in cyclopentane, if we were to look at it just as a planar molecule, there are 10 fully eclipsed carbon-hydrogen bonds that create torsional strain, 42 kilojoules per mole or 10 kcals per mole. If we pucker that into an envelope, this conformation relieves part of this strain. But an envelope conformation means that the eclipsed interactions are reduced, but the angle strain is increased slightly. So what you're seeing here is an example of trade-offs. We slightly increase angle strain, but we reduce our eclipsed interactions. For cyclohexane, the most stable conformation is a puckered conformation called a chair conformation. In a chair conformation, all bond angles are approximately 109.5, and all bonds on adjacent carbons are staggered. So if we take a notice here, right, you can actually see that these hydrogen atoms are as far apart as possible from each other. So a chair cyclohexane, there are 6 carbon-hydrogen bonds that are equatorial and 6 that are axial. And an equatorial bond extends from the ring roughly perpendicular to the imaginary axis of the ring. So if I think about having a pole going through the center of my ring, that's my axis. And anything that is parallel to that axis is going to be axial. Anything that's perpendicular to that axis, as we see in red, that's going to be equatorial. So draw 3 different representations of cyclohexane, and let's assign axial and equatorial. If we think about a boat conformation for cyclohexane, this is a puckered conformation in which carbons 1 and 4 are bent towards each other. You can see here that the boat conformation is less stable than a chair conformation by 27 kilojoules per mole, or 6.5 kcals per mole. And we can also see that torsional strain is increased by 4 sets of eclipsed hydrogen interactions. And there's also steric strain, or non-bonded interaction strain, which is created by 1 set of flagpole interactions. So this is the set of flagpole interactions, and then you can also see the set of eclipsed interactions. So if I think about how to draw a Newman projection, what I'm going to do is look at line of sight. So carbons 1 and 5 become my center carbons, or my front carbons. Then behind them are the invisible carbons 2 and 4. So carbon 2 is the large circle that's behind 1, and 4 is the large circle that's behind 5. And then you'll notice what connects carbon 1 and 5 is carbon 6. That's this carbon. Just like what connects carbon 2 and 4 is carbon 3, which is this carbon. If I look at the perspective line diagram for a Newman projection, I can also see the way that I would represent those interactions. And again, here you can see staggered, where everything is as far apart as possible, and here is where it is eclipsed. If we think about a chair flip, this is what converts all of our axial groups into equatorial groups, and all of the equatorial groups into axial groups. So if we look at the structure of the chair, as we undergo a chair flip, we actually go through several other positions: a twist boat, a boat, another twist boat, and these half chairs before we get to the flipped conformation. So notice here, everything that was axial has now become equatorial. Everything that was equatorial has now become axial. Why do we care about this? Well, this is an example of cholestanol, which is a derivative of cholesterol that's found in the human body. And you can actually see how, as you add carbon and hydrogen molecules, it quickly becomes a question of energy and optimal position to minimize interactions. So, quick recap. Chair cyclohexanes, there are 2 equivalent chair conformations. They interconvert through the boat. All carbon-hydrogen bonds that are equatorial in one chair are going to be axial in the alternative chair, and vice versa. If we have a group that's equatorial in one chair, it's going to be axial in the alternative chair. Here's what's interesting. Once I start adding substituents, then the 2 chairs are no longer of equal stability. They're going to differ by 1.74 kcals per mole. So for example, it is much lower energy to have a methyl group as a substituent be in the equatorial position than it is to have that methyl group in the axial position. Last thing we're going to talk about are cis-trans isomers. These have the same molecular formula, they have the same connectivity of their atoms, and then they have an arrangement of atoms in space that cannot be interconverted by rotation about sigma bonds. So because they're fixed, now they have a relationship with respect to each other. So here they're on the same side, which means they're cis. Here they're on opposing sides, which means they're trans. So a cyclohexane ring is commonly viewed as a planar hexagon viewed from the side or from above. Can you determine which is cis and which is trans? So this is trans 1,4-dimethyl cyclohexane and cis 1,4-dimethyl cyclohexane. We can also represent a cyclohexane as a chair conformation. So in viewing chair conformations, groups that are equatorial in one chair are going to be axial in the alternative chair. So for trans 1,4-dimethyl cyclohexane, the diequatorial chair is more stable than the diaxial chair. So here they're axial, they're both axial. Here they're both equatorial. This is going to be far more stable than when they're both axial. For cis 1,4-dimethyl cyclohexane, the alternative chairs then are of equal stability. So notice I have one that's equatorial and one that's axial, and when I flip it, I still have one that's equatorial and one that's axial. So we're going to take a look now at alkenes and alkynes. So this is kind of beginning the material that we're going to look at in a little bit more depth after you've taken your exam. So alkenes are unsaturated hydrocarbons. They contain one or more carbon-carbon double or triple bonds or benzene-like rings. So alkenes contain a carbon-carbon double bond and have the general formula CnH2n. Alkynes contain a carbon-carbon triple bond and have the general formula CN2n-2. The IUPAC nomenclature of alkenes is where we use the infix En to show the presence of a carbon-carbon double bond. If we number the parent chain to give the first carbon of the double bond the lower number, then we follow the same IUPAC rules we've been using for numbering and naming the substituents. For a cycloalkene, the numbering of the atoms of the ring must begin with the 2 carbons of the double bond. So we'll always start numbering at the double bond. Let's take a couple of examples. So pause if you need to, and go ahead and assign the names to each of these compounds. So we have 1-hexane, 4-methyl-1-hexene, 2-ethyl, 3-methyl-1-pentene, 3-methyl-cyclopentene, and 1,6-dimethyl-cyclohexene. Can you spot the mistake? Most common mistake folks make. It's right here. 1-hexane should actually be what? You're right, 1-hexene. Anytime you have a double bond, make sure that you're using the ENE at the end. So this should be 1-hexene. Some alkenes, particularly low molecular weight ones, are known almost exclusively by their common names. So things like ethylene, propylene, and isobutylene, these are what we think of as the original names of these molecules. Their IUPAC name is ethene, propene, and 2-methylpropene. Some alkenes, particularly low molecular weight ones, are known by these names. So we want to make sure that, right, we're comfortable using either term. IUPAC nomenclature of alkynes is very similar to alkenes. We use the infix YNE to show the presence of a carbon-carbon triple bond. We number the parent chain to give the first carbon of the triple bond the lower number. And then we follow IUPAC rules for numbering and naming substituents. So take a moment, go ahead and name these 2 alkynes. So 3-methyl-1-butyne and 6,6-dimethylheptine. We also have cis-trans for double bonds. So configuration is determined by the orientation of the atoms of the main chain. So if they're on opposite sides, they're going to be. If they're on same side, they're going to be. You have to determine which has the greater importance as a substituent in order to make that assignment. So here we see trans and we see cis. To assign an EZ configuration, we have to assign the priority to the substituent. So this is where I have more than 2 substituents that could have priority. So I have to go ahead and assign which is more important. So if the groups of higher priority are on the same side, then the configuration is Z or Zusammen. The groups of higher priority are on the opposite sides of the double bond, and the configuration is E or Entgegen, which means opposite. So here, the 2 highest priorities are on the same side. Here, if they're on opposite sides, then they're going to be Entgegen or apart. So how do we decide priority? Priority is based on the atomic number. So the higher the atomic number, the higher the priority. If you can't assign priority on the basis of the atoms that are bonded directly, then look to the next set of atoms, or whatever is bonded next, and that will allow you to set your priority. If you have a double bond or a triple bond, you consider them to be bonded to an equivalent number of similar atoms by single bond. So for example, if I have a double bond, this is the same as saying I have a bond to C and a bond to C. Or if I have a double bond to oxygen, that's the same as saying a bond to C and a bond to O. So take a moment and assign E and Z to the following compounds. For dienes, trienes, and polyenes, so if I have an alkene that has N carbon-carbon double bonds, each of which can show cis-trans isomerism, 2 N cis-trans isomers are possible. So consider 2,4-heptadiene. It has 4 cis-trans isomers, 2 of which are drawn here. So trans-trans 2,4-heptadiene and trans-cis 2,4-heptadiene. Why do we care? Vitamin A is an example of one of the vitamins that's common for human metabolism. Has 5 carbon-carbon double bonds. 4 of those 5 show cis-trans isomerism. Vitamin A is the all-trans isomer. And if you think about retinol versus retinal, these are 2 compounds that are essential for vision. There are some properties that are worthwhile thinking about for alkenes and alkynes. These are non-polar compounds. The only attractive forces between the molecules are dispersion forces or London dispersion forces. Those compounds that are liquid at room temperature are less dense than water. They have a tendency to dissolve in each other and in nonpolar organic solvents, and they're insoluble in water. Because water, pKa 15.7, is a stronger acid than acetylene or a terminal alkyne, the hydroxide ion is not a strong enough base for an acid-base reaction with a terminal alkyne. So why? So why is a terminal alkyne a weak acid? Well, that's because if we look at the pKa of the alkyne compared to water, we can see that this is the stronger base. Hydroxide is actually the weaker base. pKa values for alkane and alkene hydrogens are so large that no base is strong enough to remove a hydrogen from either of these classes of compounds. Just as a quick recap, what happens when phosphoric acid and water are poured into the same beaker? We have a pKa table below. And another, what happens when phenol and HCN are poured into the same beaker? And again, you can use your pKa table below. These are great examples of quiz and exam questions. Next time, we're going to be talking about the reactions of alkenes. Thanks again for your attention. We'll see you in class.